At the end of this video, you should be able to summarize Wegener's hypothesis of continental drift and describe the process of seafloor spreading. Chapter 10, Section 1, Continental Drift. One of the most exciting recent theories in Earth science began with observations made more than 400 years ago. As early explorers sailed the oceans of the world, they brought back information about new continents and their coastlines. Map makers used the information to chart new discoveries and to make the first reliable world maps. As people studied the maps, they were impressed by the similarity of the continental shorelines on either side of the Atlantic Ocean. The continents looked as though they would fit together like parts of a giant jigsaw puzzle. The east coast of South America, for example, seemed to fit perfectly into the west coast of Africa. Wegener's hypothesis. In 1912, a German scientist named Alfred Wegener proposed a hypothesis that is now called continental drift. Wegener hypothesized that the continents once formed part of a single landmass called a supercontinent. According to Wegener, this supercontinent began to break up into smaller continents about 250 million years ago, which was during the Mesozoic era. Over millions of years, these continents drifted to their present locations. Wegener speculated that the crumpling of the crust in places may have produced mountain ranges, such as the Andes on the western coast of South America. Fossil evidence. In addition to seeing the similarities in the coastlines of the continents, Wegener found other evidence to support his hypothesis. He reasoned that if the continents had once been joined, fossils of the same plants and animals should be found in areas that had once been connected. Wegener knew that identical fossils of Mesosaurus, a small extinct land reptile, had been found in both South America and Western Africa. Mesosaurus, a fossil of which is shown on the screen here, lived 270 million years ago during the Paleozoic era. Wegener knew that it was unlikely that these reptiles had swum across the Atlantic Ocean. He also saw no evidence that land bridges had once connected the continents. So he concluded that South America and Africa had been joined at one time in the past. Evidence from rock formations. Geologic evidence also supported Wegener's hypothesis of continental drift. The ages and types of rocks in the coastal regions of widely separated areas, such as Western Africa and Eastern South America, matched closely. Mountain chains that ended at the coastline of one continent seemed to continue on other continents across the ocean, as is shown on the screen here as well. The Appalachian Mountains, for example, extend northward along the eastern coast of North America, and the mountains of similar age and structure are found in Greenland, Scotland, and Northern Europe. If the continents are assembled into a model supercontinent, then the mountains of similar age fit together in continuous chains of mountains. Climatic evidence. Changes in climatic patterns also suggest that the continents have not always been located where they are now. Geologists discovered layers of debris from ancient glaciers in southern Africa and South America. Today, those areas have climates that are too warm for glaciers to form. Other fossil evidence indicated that tropical or subtropical swamps covered areas that now have much colder climates. Wegener suggested that if the continents were once joined and positioned differently, evidence of climatic differences would be easy to explain. Missing mechanisms. Despite the evidence that supports the hypothesis of continental drift, Wegener's ideas were strongly opposed. Other scientists of the time rejected the mechanism by which Wegener proposed that the continents moved. Wegener suggested that the continents plowed through the rock of the ocean floor. However, this idea was easily disproved by geologic evidence. Wegener spent the rest of his life searching for a mechanism that would gain scientific consensus. Unfortunately, Wegener died in 1930 before he identified a plausible explanation. Mid-ocean ridges. The evidence that Wegener needed to support his hypothesis was discovered nearly 2 decades after his death. The evidence lay on the ocean floor. In 1947, a group of scientists set out to map the Mid-Atlantic Ridge. The Mid-Atlantic Ridge is part of a system of mid-ocean ridges, which are undersea mountain ranges through the center of which run steep, narrow valleys. While studying the Mid-Atlantic Ridge, scientists noticed 2 surprising trends. First, they noticed that the sediment that covers the seafloor is thinner, closer to a ridge than it is farther from the ridge, as is shown on the screen here. This evidence suggests that sediment has been settling on the seafloor farther from the ridge for a longer time than it has been settling near the ridge. Scientists then examined the remains of tiny ocean organisms found in the sediment to date the sediment. The distribution of these organisms showed that the closer the sediment is to the ridge, the younger the sediment is. This evidence indicates that rock closer to the ridge is younger than rock farther from the ridge. Second, scientists learned that the ocean floor is very young. While rocks on land are as old as 3.8 billion years, none of the oceanic rocks are more than 175 million years old. Radiometric dating also showed evidence that seafloor rocks closer to a mid-ocean ridge are younger than seafloor rocks farther from a ridge. Seafloor spreading. In the late 1950s, a geologist named Harry Hess suggested a new hypothesis. He proposed that the valley at the center of the ridge was a crack, or rift, in Earth's crust. At this rift, molten rock, or magma, from deep inside Earth rises to fill the crack. As the ocean floor moves away from the ridge, rising magma cools and solidifies to form new rock that replaces the ocean floor. This process is shown on the screen here. Robert Dietz, another geologist, named this process by which new oceanic lithosphere, which is seafloor, forms as magma rises to Earth's surface and solidifies at a mid-ocean ridge as seafloor spreading. Hess suggested that if the ocean floor is moving, the continents might be moving too. Hess thought that seafloor spreading was the mechanism that Wegener had failed to find. Still, Hess's ideas were only hypotheses. More evidence for seafloor spreading would come years later in the mid-1960s. This evidence would be discovered through Paleomagnetism, the study of magnetic properties of rocks. At this point, you should be able to summarize Wegener's hypothesis of continental drift and describe the process of seafloor spreading.